people gone. If there's no dipoles on it at all, like CH3, that molecule, no matter what, is nonpolar, for sure. All right? But all those other ones, if you drew a dipole, that means there's polar bonds in that molecule. Now the question is, based on the shape, is the molecule itself as a whole, is the molecule polar? So most of the ones on this sheet, there are some polar bonds that exist. The question is now, is the molecule polar? Yesterday, when I showed you the little barrette dealy job, I talked about how the water molecules line up because one side is positive and the other side's negative, and they're able to line up and be attracted to that negative piece of plastic. If a molecule can line up like that, where one side is positive and the other side is negative, that makes it polar. If a molecule cannot line up like that, where one side is positive and the other side is negative, that makes it nonpolar. It would actually spin in an electric field, or when you put up a negative charge next to it, it would not line up. Water did yesterday, and all get attracted to one side. All right? In the case of yesterday, we just had a negative charge. If we would have put a positive side on the left, all of them would have just sat in the middle and, but been lined up. We could imagine them coming out and have that ultimate superpower, and imagine those molecules coming out of the barrette all lining up this way, as one side's attracted to the negative and one side's attracted to the positive. So, how do we determine that? Well, we need to take a look at the shape. The shape is important. All right? Let's start with basic. Basic. Jim, could you stand up? Jim and I are both oxygen atoms. Both oxygen atoms. What's our difference in electronegativity? 0. Do we have a dipole? No. Can we be polar? No. Automatically, you have no dipole. It's a nonpolar molecule, for sure. Thank you, Jim. That was very helpful. Now, let's say that we have a different molecule. We have different atoms. For instance, HCl. Looking on our electronegativity, Cl is more electronegative. So the Cl will have a negative charge. Marissa will be the positive. You'll be H. Can you stand up, please? And I'll be the negatively charged chlorine. We have a bond. We are a molecule. Is there one side of the molecule that's negative and another side that's positive in this case? Yeah. So we don't not only have a polar bond, but the molecule itself also is positive on one side, negative on the other side. So we have a polar molecule. Questions so far? Let's change it up a little bit. Oh, you can keep that on. Keep it on. Let's change it up a little bit. Now let's put one that's on your sheet again. Kayla, go ahead and stand up. We're going to keep it linear. But we're going to go to CO2. If we look on our electronegativity sheet, the oxygens are more electronegative. It looks like this. So Marissa will stand in the middle. She's the carbon. We're negatives on the outside of her in equal and opposite directions. Who has the electrons around them? Marissa in the middle or us on the outside? Outside, because we are oxygens, which are more electronegative. So I and Kayla have more electrons around us than she does. So the dipole's pointing out towards us. But these two dipoles, one pointing towards me, one pointing towards Kayla, cancel each other out. There's no one negative on one side and one and only on one side. they're in equal and opposite directions right now. So as a molecule, even though we have polar bonds here, and they have polar bonds over there, this molecule is nonpolar. Because these will cancel each other out, essentially. One side can't be negative and the other side positive based on this shape. Shape's very important. All right? Let's change it up a little bit. And Kayla, actually Brandon, come on up. And Kayla, you can sit. So now let's imagine it's water. I'll put this up here also. Water. What shape is water? Bent. Oxygen's partial negative because it's like this. And hydrogens are partial positive. So now I'm going to be the oxygen. They're the hydrogens. Our shape is bent. Are there positives on one end and a negative on the other of this molecule? There are now, just like the water we talked about yesterday. There's positives on that side of the molecule, negative on this side. That makes the molecule polar. Questions so far? Because of that, most bent molecules will be polar. The only exception would be if the electronegativity between us was less than 0.3. Well, then we have to be polar. So it's water, the difference is more than 0.3. Let's take it one more step and go into all the different types of shapes. We won't do them all up here. So let's talk about BCl3, because BH3 we know has to be nonpolar because the difference is less than 0.3. BCl3 on the back of your sheet, you drew dipoles pointing towards the chlorines. All right? So Marissa will be in the middle. Bailey E, come on up. I didn't put another negative, so we're just going to make an assumption here. She's negative. Okay? She's negative. Marissa's in the middle, positive. Move over there a little bit, Brandon, so we make this trigonal planar look. So we're all negative to the outside. She's positive in the middle. Is there a part of us, is there one side of the molecule that's negative and another side positive? No. It's all evenly distributed, isn't it? Negative, 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 all in equal directions. So now, this is again, the trigonal planar is going to be nonpolar because we have all equal directions. Sure, you might say, well, Bailey, and you are negative. Yeah, but so is the other side of the molecule. Or Brandon, you're negative. Yeah, but so is the other side of the molecule. So it's not one side or the other. Now, Marissa, stand up on there, please. And now let's make a trigonal pyramidal. She's positive. She's up in the air. We're all negative. Can we be polar now? We can, because the ground is negative and up in the air is positive. We have a separation of charge now. Now there's one part of the molecule that's one and the other part that's the other. Let's throw Matt up in the ceiling. And he's also negative like we are. So let's make it tetrahedral. If he's negative like we are, and he's up in the ceiling, polar or nonpolar? Yeah. It's got to be nonpolar, folks, because now we have an even distribution, and there's no one part of the molecule, even though you might say, well, the whole bottom was negative, just like before. Yeah, but Matt's negative up there, too. There's no one side of the molecule that's negative or positive now. So tetrahedral is pretty much always, as long as all the atoms out here are the same. We're not going to get any more intense than that, but as long as all the atoms out here are the same. Let's say she was a carbon and the three of us were hydrogens, and then Matt was up there as a fluorine. That would actually be a polar molecule. But we don't need to get into that here. That's an AP topic. Okay? But this trigonal pyramidal is polar. Almost always. Tetrahedral, almost always nonpolar. Once you start throwing in different atoms on the outside, things change a little bit. What do you think about trigonal, bipyramidal, and octahedral? Marissa, you can get down. Thank you for doing that. So we look at these two. What do you think, just looking at their shapes? Why do you think they're nonpolar, John? Exactly. You can't make one side of this molecule positive or negative because they're all evenly around them, around that central atom. All right? What I'd like you to do now is, based off of that information, I want you to try to identify everything besides POCl3 as polar or nonpolar with your group. Identify what on that worksheet is polar or nonpolar based on our little discussion right there.